So hi, welcome. I'm Ari Chada. I'm a data science intern with CosmiQ and an undergraduate at Dartmouth. And today we'll be looking at multifaceted object detection with RarePlanes using YOLOv5. And there's been a lot of work in the object detection sphere simply recognizing objects, mostly in photographs. But today we'll look to take it a step further and see if we can discern sub-characteristics of objects using custom classes. And so basically, you'll be looking to create images like these. This was taken from Fort Lauderdale Hollywood Airport in Florida, and these planes are classified by what you'll be doing today, which is the number of engines and the propulsion type. And so before we dive in, a little bit about who we are. CosmiQ Works is an applied research lab that's focused on geospatial analytics and supporting sort of all facets of that process, whether that be through applied research, applying computer vision techniques to remote sensing data, or through our LLC SpaceNet, which sponsors the creation and the release of open source datasets and algorithms through our SpaceNet challenges. We've also created several open source software packages that can be found via our GitHub, the main one being Solaris to simplify spinning up and creating your own machine learning pipelines using remote sensing data, as well as others focused on road network extraction, object detection, and time series analysis. And last but not least, we also provide market analysis to our partners on the industry. So now let's dive into the tutorial itself. The dataset we'll be using today is one we created in June of 2020 called RarePlanes, which, as you probably guessed already, is a meticulously tagged and curated dataset of plane imagery, mostly around airports. And so here we have a traditional machine learning workflow from left to right. The RarePlanes dataset touches on a few parts of these very specifically, mostly the data requirements aspect, label and taxonomy, as well as what this tutorial addresses, which is the testing and evaluation piece, as well as the ongoing development of the dataset itself. And today we're going to be looking at that last piece in depth and trying to see if we can identify sub-attributes of aircraft. And so RarePlanes is unique for a couple of reasons. Foremost, that it is the largest openly available dataset using synthetic data. And so the top half of this image, or this collection of images, is real data taken from satellites and tagged, and the bottom half is actually created by one of IQT's partner companies, AI Reverie, which creates synthetic data. And this data comes from a wide range of geographic locations, and they exhibit a wide variety of weather conditions. One more thing to note here, though, is that these images are tiled, meaning that for the most part, they focus on plane instances. We'll be using a collection of real tiled images today, so really only the top half of this image in our tutorial, primarily because the images themselves in their large form are too large to use with our networks. But it's important to realize that these images come from larger images like these. And you can probably recognize this one from the image I showed you before. This is, again, Fort Lauderdale Hollywood Airport in Florida. And so now I mentioned earlier that RarePlanes is unique for a variety of reasons. The second of which is sort of the crux of our study today, and that's the dataset taxonomy. So not only are all the planes in the dataset tagged by 11 subattributes, you can also create custom classes that combine these attributes, whether that be looking at wing shape and length together, or the number of tail fins with the roller type of the aircraft, or what we'll be doing today, which is combining the number of engines and the propulsion type. And so the model we'll be using today is You Only Look Once, or YOLO as it's commonly referred to. And YOLO is special for a variety of reasons. Foremost, because it's sort of significantly faster than a lot of its peer object detection networks. As you can see in the graph in the top right, it's kind of off the graph. This is from the YOLOv5 paper. Not only that, we've used it quite a bit in our object detection work, different versions of YOLO and also YOLT, and we've seen impressive performance both in the speed of the model as well as its accuracy. And because YOLO is so fast, it works in almost real time. So it's been used in a lot of video data as well. And today we'll be using Ultralytics' implementation of YOLOv5, sort of the most recent of the YOLOs. And we selected YOLOv5L, which on this graph you can see is the green one. And that's mostly because it kind of had, so all these models were calibrated using the COCO dataset, and they were tested trying to see how they maintained their speed as well as their accuracy. And we felt that YOLOv5L had a good balance of the two, and it seemed to work well for this task. So to the tutorial itself, you can spin it up in one of two ways, either through the Amazon machine image or the Docker container, if you have your own GPUs. Both of these are heavily detailed in the README of the GitHub for this tutorial. With the Amazon machine image, we take care of a lot of the initial steps. But if you'd like to sort of do your own pipeline, you can also spin it up pretty easily on your own GPUs. And so this tutorial is composed of 4 different notebooks. The first being the pre-processing notebook, in which you'll create custom classes, create the YAML files that are specific to YOLO, and then create YOLO labels that sort of give you the width, height, class, and XY position of all the attributes in each image, so that YOLO can interpret them. And then next, you'll be looking at training the model and running a preliminary inference. And this implementation of YOLO is great because it kind of simplifies these 3 aspects for you through 3 Python scripts. The first being train.py, and we trained, or you basically run these through a single bash command, and we chose to train our images, our model via 100 epochs with a batch size of 36. And then detect.py is sort of preliminary inference on the tiled images. And this, again, is run through a simple bash command, and it takes a couple of minutes on 2,700 images, which is pretty impressive. And then last but not least, test.py, which is evaluation on the tiled images. So it's not as robust as if you were to evaluate on the sort of whole airfield images themselves. But it gives you sort of a preliminary barometer of how your model did. And so the rest of this pipeline then looks to take those tiled images, convert them to sort of back to the larger airfields, and then run model scoring so that you've gotten rid of those redundant aircraft that may not have been labeled appropriately, or maybe only half of one is in one of the tiles. And so you usually get a little bit of a performance boost once you stitch them back together. And so that takes us to notebook 3, in which we'll stitch together the tiled GeoJSONs and then run another round of non-max suppression on the images. And then last but not least, model scoring, where we'll look to create custom classes for the ground truth, convert ground truth to bounding boxes, and then calculate F1 recall and precision to see how our model did. And so let's dive in. And so before we start, one important thing to note is YOLO is very specific on how it wants its data to be organized. And so we've already taken care of this if you're spinning up the AMI, but if you're doing this in a Docker container, I thought I'd show you how the data is organized so you can do this yourself. And so I've created this directory class1, and if we dive in there, you can see that you have 2 subdirectories, images and labels, and then within images and labels, you have a train and a val. Val is what YOLO calls test. They're essentially the same thing. And within these directories, you'll be putting your images for training and testing. And you'll have to make sure that they're organized exactly like this. And you'll do this sort of before you spin up your model. And then during the pipeline, you'll be creating your labels. And those, again, I would just make 2 dummy directories that are train and val. Ignore the caches. Those are sort of created during training. And then from there, you can sort of spin up a model yourself. And so once you have your data organized like this, make sure you've cloned the repository, and then launch your Jupyter notebooks from the YOLOv5 directory. And so we'll start on that first notebook. And so a few imports, you can ignore these depreciation warnings. And then that first step is creating custom classes. And so as I mentioned before, you can sort of combine any of the attributes, sub-attributes we listed before into anything you want to do. We chose engines and propulsion, a number of engines and propulsion type, because we thought there would be sort of a boost in accuracy of identifying those two things by sort of forcing the model to look at them. But you can pick whatever's interesting to you, or if you think that combining two different attributes would make for a more meaningful conclusion, you can do that as well. And so these functions are taken from the AI Reverie's RarePlanes GitHub, which contains a lot of helper functions for the data set. And we use a couple of them in this pipeline as well. And then, of course, just specifying your file paths to where the GeoJSONs are, your training and test GeoJSONs, and then where you want to be outputting your custom classes. And then here you're just specifying what the custom classes are, and then of course running the function with all this information. And then the next step here is creating your YAML files. So as I mentioned before, the YAML files kind of tell YOLO where everything is and how to pull it. And so here, if you run this, you'll sort of get all your different class types as well as the number of classes. And so you want to put both of these pieces of information in your YAML files. And so I can just show you where that is now. So you'll be editing two YAML files. We've done this already if you're using the AMI, but if you're using the Docker container, or if you want to change and use a different custom class, you'll be doing this here. In that, I usually just open up the YAMLs with VI just because it's simplest. And so the first part of this YAML is telling it where the training data is. That's in that directory that we walked through before, where we put all the training data once we downloaded it from S3. Or if you had the AMI, then we've done that for you. And then telling it where the test or the validation data is, telling it the number of classes, which was that second number we output, and then the names of the classes, which was that list. And then getting out of here, you'll want to edit one more, and that is models. And so we picked YOLOv5L, so we'll just hop into there quickly, and you're only editing one thing. And that's the number of classes, and so we've made that 8 as well. But if you're sort of using a different set of classes, that number will change. And then our next step, of course, is creating those YOLO labels so that now YOLO can tell what instances are in what images and process it from there. And so you'll just run this function. You'll sort of tell it where all the information it needs is, as well as creating your directories for your output. And then run this. This top one's for the training data, and this bottom one is for the testing data. And then next, onto the second notebook. So the second notebook is our model training and our preliminary inference. As I said, pretty simple bash commands here with a number of different attributes. Sort of the important ones to focus on are batch size, and your goal is really just to fill up your GPUs to speed up training. And if you get that sort of NVIDIA error of the memory's full, first try reducing your batch size before you try something more invasive. And then we chose 100 epochs. We sort of found the model converged typically around 80, but depending on what you're doing, if it's a little more complex or less complex, you can edit that number as you like, and then telling it where those YAMLs are that we created earlier. And then you should be good to go for the most part. And training takes quite a bit of time. It took 4 to 5 hours using the EC2 machine that we have for the AMI. And then once you've run training, we just kind of move the dummy file name that it creates to something a little more meaningful so we can use it later on. We know exactly what we're using. And then running that next script, which is detect.py, which is our inference pipeline. And here again, you're telling it a number of things. Foremost, you're giving it the best weights from the training run. And so YOLO saves each one, but it also saves the best weights, and so you'll take that. And then from there, the images themselves are 512 by 512, and so you should make sure you include that. And then the confidence threshold, trying to run sort of a first round of noise filtering. And so anything with a confidence below 0.4, we kind of exclude. And then last but not least, you're going to want to make sure you have this save text field on because you'll be using that later. And then moving the inference output just to something more meaningful again, and you can change that name as you like. Just make sure you keep it consistent throughout. And then last but not least, running test.py, and this gives you kind of an initial barometer of how your model did. That being the other interesting thing it tells you is the number of targets of each class type within within your results. Sorry. And then it also gives you your precision, your recall, and your mean average precision. And of course, most of these numbers should go up as you sort of run the non-max suppression and reevaluate in the next two notebooks. So let's dive into that third notebook. And so YOLO RarePlanes post-processing, and again, you're just importing a variety of things. And then you'll want to run non-max suppression. We have an overlap threshold of 0.5 just to exclude instances that are like identifying the same instance in different images. And from there, you'll run this function. You'll tell it where everything is. And this is just sort of your lookup table to make sure you have everything right. And then you'll run this script. And this script will, and if you're using different classes, you'll want to change this line. But for the most part, you'll create your CSV, and then you'll run your non-max suppression here. And you should have destroyed all, most of the repeat instances. And then last but not least, diving into that last notebook of scoring the model. And so in order to score the model, we need to convert the ground truth into something that's the same as our inference output. And so we have our diamond annotations from the data set, and now we'll want to convert them to bounding boxes. And so you'll do that in this script here, telling it where everything is, telling it where to output your bounding boxes, and then saving those. And then next, we'll have to take the GeoJSONs we created of our bounding boxes and now create our custom classes with the ground truth. And so now we can compare apples to apples, essentially. And so you'll do that by running this function. You'll tell it where everything is again, and then also, again, creating the same custom class. And then finally onto creating those results or identifying those results. And again, you're telling it where the bounding boxes for your inference are that we created, and then you're telling it where the ground truth is, and it'll run this function, and it'll come up with your F1, your precision, your recall, and these are your total recall, precision, and F1. But as you probably saw with train.py, there were sort of several classes with very few instances. And so these total numbers don't mean as much as if you were to do it class by class. And so this last cell we have here just takes it and breaks it down class by class. And so you have a meaningful output. And I'm actually running this on a subset of the data. And so your results should be a little better than mine once you run it on the whole thing. But as you can see, the ones we had few targets of, like the 0, no engines, and unpowered propulsion, so those are your gliders, as well as the three engines with the jet, we sort of have poor performance on. but common planes in the data set, we did pretty well across the board. And so now you've essentially finished the tutorial, and we can go back to our PowerPoint. And so in summary, what we've done here is we've pre-processed the images. We created our custom classes. We created those YAML files, and we created those YOLO labels. Then we trained our model after sort of telling it where everything was. We performed preliminary inference and scoring. And then we ran another round of non-max suppression, transformed the ground truth for comparison, and then calculated our F1, our precision, and our recall. And as some of our outputs here across different airfields. And so where is everything located? These links should be in the description, but you can find the code base for those RarePlane helper functions on the AI Reverie's GitHub under RarePlanes. The tutorial you can find there. The user guide you can find on our website under RarePlanes, and then the data set is hosted on AWS S3 under RarePlanes Public, and then AI Reverie, our partner creating the synthetic data. You can visit them, and then of course us on CosmiQWorks.org.